Assalamu alaikum and a very good day everyone. I am Abila Hena Anayat and today I will be sharing my understanding with you for the question number 1. The question number 1 states that the traffic volume data were obtained in an observation on a section of rural highway in Kolang, Johor for the period of 120 minutes, and it requires us to answer the following questions. A. The average hourly volume. B. The rate of flow for the time interval. C. The maximum hourly volume. And D. The 15 minutes interval with the highest volume. And lastly E. Which is why is the rate of flow higher than the maximum hourly volume. Now, let us proceed into the answering session. Before starting this session, we need to find out the rate of flow. The rate of flow is equals to the interval volume multiplied by 60 divided by the time interval. For the time interval here, we will take 50. Now we will proceed to answering the average hourly volume. For the average hourly volume, we need to add the total rate of flow divided by the total number of datasets, which is 8 in this case. So after adding the total rate of flow and dividing it by 8, we will be able to find the average hourly volume. For the part B, which is the rate of flow, we will take into consideration the interval volume multiplied by 60, which is the time for 1 hour divided by 15 minutes. So for the part C, which is the maximum hourly volume, we have 5 cases to consider here. The first one is from 8 to 9 am, followed by 8:15 to 9:15, 8:30 to 9:30, 8:45 to 9:45, and lastly 9 to 10 am. So after calculating the maximum hourly volume for all the time intervals, we are able to see that the data set for 8:45 to 9:45 is the maximum in our case, which is 457 vehicles. After answering the questions A to C, we are able to understand two main concepts, which are the hourly volume means the number of passenger car equivalents during any period of 60 consecutive minutes, and the peak hour volume is the volume of traffic that uses the approach lane or lane group in questions during the hour of the day that observes the highest traffic volumes for that intersection. Now let's move on to the question number D, which is the maximum 15 minutes interval with the highest volume. From the data sets given, we are able to see that the maximum rate of flow is for the 8:45 to 9 am vehicles, which is 572 vehicles. Now we will be moving on to the question number E. For the question number E, we need to understand that traffic engineers focuses on the peak hourly volume in evaluating the capacity and other parameters because it represents the most critical time period. And also, as any drivers who travels during this morning or evening rush hour knows, it's the period during which the traffic volume is at its highest. So here, the rate of flow is higher because the number of vehicles passing per unit of time is greater compared to the hourly volume, which means the driver experiences heavy traffic flow and insufficient traffic control systems at junctions. Kindly note that the maximum rate of flow considers the worst situation on the road, while the maximum hourly volume only considers the maximum number of vehicles that goes to a particular point in an hour. And this is why the rate of flow is higher than the maximum hourly volume. That was all for my talk. Thank you everyone for your time and attention.
Hello and Assalamu alaikum. My name is Abdullah Mukhtar Batura and I will be discussing question 3 for this video. So the table below describes the sample of travel time and vehicle stop delays obtained from the total volume of traffic on major roads leading to the city center. The length of the road section tested was 5 kilometers. Calculate the average travel speed and running speed based on the information given. Also, determine the average delay based on the running speed if the free speed limit is 70 kilometers per hour. So from this question, our objective is to obtain the average travel speed and the average running speed based on the information given, which is journey time, the delay, and the number of vehicles. Also, we had to determine the delay based on the running speed if the free speed limit is 70 kilometers per hour. Okay, so let's look at the formulas we're going to use. First up, the average travel speed formula is equal to the distance divided by the journey time. Distance is given as 5 kilometers for basically every formula. The journey time is given in the table. The average running speed is equal to distance divided by running time. Running time is the time that the vehicle is actually in motion. Therefore, the running time is journey time minus the delays. So we move on to a new formula, which is average running speed equals distance divided by the journey time minus the delays. For the average delay parts, we tweak the first formula into making delays the subject. Therefore, we get journey time, average delay equals journey time minus the distance divided by the average running speed. So this is the calculation for the first part, which is the average travel speed in kilometers per hour. So let's take example journey 1. Distance is 5 kilometers, time taken is 8. Time taken is 8, but the time taken is given in minutes, therefore we have to convert it into hours, so we do 8 divided by 60. After that, we get our travel speed 37.5 kilometers per hour. Same thing for journey 2. Let's look at journey 3. Journey 3 also is equal to distance divided by time taken, so 5 distance divided by 7 time taken, divided by 60 in order to convert it into hours, we get 42.9 kilometers per hour. And then for the average running speed is average running speed formula is given as distance divided by journey time minus delays. So let's look at journey 5 for example. The average running speed is distance 5 divided by 8.3 divided by 8.5, which is the time taken, minus 3.6, which is delay time, divided by 60 in order to convert it into hours. We get 61.2 kilometers per hour. Use the same formula for every journey, and we get the average running speed for each journey. So the final average travel speed, we add all of them, then divide by 6, which is the amount of journeys. We get 38.6 kilometers per hour. And for the average running speed, we add all of them, then divide by 6, we get 77.6 kilometers per hour. So since the travel speed is much less than the running speed, actually by half, it is less than it by half, the road experiences more than the average traffic flow. Therefore, checks should be performed for improving the traffic quality. We can improve the traffic quality by increasing the number of lanes of the road, or by increasing the amount of time given for green lights for road users to pass on that specific road, or on the specific route. That's what I mean. Okay, let's go on to the average delay. So for calculating the average delay based on running speed, if the free speed limit is 70 kilometers per hour. The average delay equals journey time minus the distance divided by the average running speed. So looking at journey 1, the average delay is equal to the journey time, which is 8 minutes, minus the distance, which is 5 kilometers, divided by the average running speed, which is 70 kilometers per hour. Then we divide by 60 in order to convert it into kilometers per minute, because we want our answer in minutes. Therefore, we get 3.7 minutes as the average delay time. Let's look at journey 4 now. So the journey time in journey 4 is 6.5, and the distance is 5 kilometers. The distance is 5 kilometers. Average running speed is 70 kilometers per hour. Then we divide by 60 in order to convert it into kilometers per minute. We get 2.2 as our average delay in minutes. So for the final average delay, we add all of them, divided by 6, we get 3.6. And the average delay at individual journey speed, which we obtain from the table, is 3.3. Therefore, this goes to show us that even though the speed is more or less the average delay, the delay wouldn't really change based on the speed. Something else has to be changed in order for the delay to change, and it is not the speed, because the speed doesn't concern the delay. Okay, this is after we tabulate all the values, putting them in the table, and this is what we get in the end. So thank you, and let's move on to the next question. Assalamu alaikum.
My name is 3842 and I'm going to explain how to solve this question 5. So let's see the question. In one traffic flow, 30% of the total vehicles move at a constant speed of 60 km per hour, 30% at a speed of 80 km per hour, and the rest at a speed of 100 km per hour. An observer vehicle moving at a constant speed of 70 km per hour with a cut on for 5 km and cut by 17 vehicles more than the number it cut. When the observer moves against the current at the same speed and distance, the number of vehicles found is 303. First question asks to determine the traffic flow rate and its mean speed. The second one is to calculate the number of cars moving at a speed of 100 km per hour that overtaken the observer vehicle. Okay, so this is the illustration of the question. This is the observer vehicle that travels at a constant speed of 70 km per hour. The question said that the observer vehicle is cut by 17 vehicles more than the number it cut. Okay, so let's say P, which is the number it cut, as X, which is the variable that we don't know. And so the number of vehicles cut this observer vehicle would be 17 plus X. And so NAB here is the number of vehicle in the opposite direction, which is 303. Okay, so in one traffic flow, 30% of the vehicle moves at a constant speed of 60 km per hour, another 30 at speed of 80 km per hour. So in one traffic flow, the total percentage of the vehicles is 100. So the percentage that moves at a speed of 100 km is 100% minus 2 times 30, which equals to 40%. Okay, next let's see the solvings. The first one is traffic flow rate, which is Q. Q equals to NBA, which is the number of vehicles in opposing direction from B to A, which is 303 plus O minus B. O is the number of vehicles that overtakes the observer vehicle, which is 17 plus X, minus P. P is the number of vehicles it overtakes, which is X, divided by TAB. TAB is the time taken from A to B, plus TBA, which is the time taken from B to A. So finally we get the answer of traffic flow rate is 2240 vehicle per hour. The second one is mean speed, which is U. And the equation we use for U is L, which is the length of the road from A to B, which is 5 km per hour, divided by TAB, which is 5 over 70 minus O minus P divided by Q. And finally we get the mean speed is 17.32 km per hour. Okay, moving on to the next question. The number of cars moving at a speed of 100 km per hour that overtaken the observer vehicle. Here we use the equation of the relationship between Q, U, K. So by rearranging the formula, we got K equals to Q divided by U. As we got from the previous slide, Q is 2240 and U is 17.32. So we got K, which is the density, is 28.6 vehicle per kilometer. Okay, so since the percentage of vehicle traveling at a speed of 100 km per hour is 40%, therefore the number of vehicles that overtaken the observer vehicle is K times the length of the road, which is 5, times the percentage of the vehicle traveling at a speed of 100 km per hour divided by 100. So finally we get the answer of 57 vehicle. So that's all. Thank you.
Assalamu alaikum wa rahmatullahi wa barakatuh. Dan Salamat Sajitra. I'm Muhammad Arshad and today I'm going to explain question number 7. So let's get started. So let me read the question. So the question is, the maximum free speed of a road is 80 km per hour. The current traffic flow is 1200 vehicles per hour with 60% private vehicles, 20% commercial vehicles and 20% buses. The average distance between vehicles by type in a stagnant flow condition is 8 meter for private vehicles and 12 meter for commercial vehicles and buses. The occupancy rate of private vehicles is 2 persons per vehicle and buses are 35 persons per bus. The relationship between speed and density is linear. If the use of private vehicles is restricted, almost half of private vehicle users will switch to buses. So now the question from this is determine first the maximum possible flow capacity of the road in question before user transfer takes place. The second part is the maximum possible flow capacity of the road in question after the transfer of users take place, and last but not least the average speed of traffic flow before and after the user migration. Okay, so in order to tackle the first problem, we need to know two parameters in order to calculate maximum possible flow capacity Qn. For that we require UF, which is the maximum free flow speed, and the jam density Kj. So in order to find density, which is K, we need to, since we are not provided with the data, we need to calculate the density from the spacing given. So first we need to calculate the average spacing. Since we know the proportion of each category of vehicles, using that proportion, we can find the average spacing by using this formula. S is equal to 0.6. 0.6 refers to 60% of private vehicles and 80 meter is the distance between the private vehicles, plus the 0.2, which is 20% into 12, which is the distance between consecutive commercial vehicles, and similarly goes with the buses as well. So after calculating, we found that the average spacing per vehicle is 9.6 meter per vehicle. So using this value, we can then find the density K, which is equal to 1 over 9.6 into 10 raised to minus 3. 10 raised to minus 3 refers to the unit conversion from meter to kilometer. So based on the calculation, we found out that the value of density is 104.17 vehicle per kilometer. Now then, using the flow density relationship and the equation, Q is equal to UFK minus UF by kg into K square, we can substitute all the values that are given plus the density we have just found out. So basically Q is 1200 vehicle per hour, and then UF, maximum free flow speed, is 8 km per hour, and the K, which is calculated just now, is 104.17 vehicle per kilometer. So substituting this, we found that the Kj, which is the jam density of the road, is 121.69 vehicle per kilometer, which we can approximate to 122 vehicle per kilometer. Therefore, now the maximum flow capacity before the user transfer can be calculated as Qm is equal to UF multiplied by Kg divided by 4, which is 121.69, which is the UF, 121.69, which is the Kj, multiplied by UF, which is 80, divided by 4. So the total value will be 2433.8, which can be rounded off to 2434 vehicle per hour. So this is the maximum flow capacity before the user transfer takes place. Now the second part of the question, we need to find the same value, which is the maximum flow capacity, but now in this scenario after the restriction took place. So according to the condition, when there is a restriction, almost half of the private vehicle users will have to switch to bus. So that means based on the previous flow volume, which is 1200 vehicle per hour, we got to know that 60% of it comprises of cars. So from that data we can get that the composition of each vehicle. So as you can see here, before there was around 720 cars. So now, since almost half of the private vehicles users will have to switch to bus, so it just says almost, it does not mention half. So we find the cars which will be running after the restriction, which can be calculated as 720 divided by 2, which is half, plus 1 extra, so it will become 361 cars. Now then, since we know that the occupancy rate of each vehicle is 2%, so since 359 buses got reduced in this transfer, so we need to accommodate those people into the buses. So initially they were around 20% of 1200 vehicle per hour, which is 240 buses, and now there are 359 car users who are going to be shifting to the buses. So for that we need to now calculate the number of extra buses after the transfer takes place. So that will be 359 cars into 2, so that many amount of users, which is approximately around 718 divided by the occupancy rate of bus. So each bus is occupied by 35%. So it comes around 20.5, which can be approximated as 21 extra buses. Now using the above data, we can calculate the new flow. So new flow will be 361 car users plus 240 plus 21, which is 261 buses, and then we have the old commercial vehicles, which is around 20% of 1200, so which is 240. So when you sum it up, you get a value of 862 vehicles per hour. So this is the new queue. So now based on that, we need to find the new average spacing in order to calculate the density. So the new average spacing can be found as by taking the proportion of each vehicle composition over the total vehicle per hour queue. So 361 divided by 862 into 8. 8 meters is the stagnant flow spacing between consecutive private vehicles, and then since both commercial vehicle and buses have a spacing of 12 meters, so I summed it up. So the overall the leftovers, so how the vehicles which are not private vehicles divided by the total flow multiplied by the distance which is between consecutive buses or the consecutive commercial vehicles, which is 12 meters. So when you find when you sum this up, you get the average spacing value, which is 10.32 meters per vehicle, which is slightly higher than the previous scenario. So now the new density K can be calculated as 1 over 10.32 into 10 raised to minus 3, which is conversion from meter to kilometer, from meter to kilometer, and then that value is found out to be 96.9 vehicles per kilometer. Now then, we can use the simple formula Q is equal to UK, which is flow is equal to speed into density, to find the speed of the average speed of the vehicles, which is 8.9 km per hour in the congested flow. Now then, using the linear relationship between speed and flow, which is U is equal to UF minus UF by kj over k, substituting the above values, which is U, which is 8.9 km per hour, which is just found out using Q is equal to UK, and UF we all know that it is 80 km per hour, and then UF over kj. So the kj is the unknown value here, and then k we just found out from the average spacing. The k new is 96.9 vehicles per kilometer. So using those values, we can find the new jam density to be 119.02 vehicle per kilometer. Therefore, now the maximum flow capacity QM after the transfer of passengers from cars to buses can be calculated as UK or multiplied by kj over 4, which is UF multiplied by kj over 4, which is 80 multiplied by 119.02 divided by 4, which is 2180.4, or it can be rounded off to 2181 vehicles per hour. So as you can see that the maximum flow capacity has slightly decreased when in comparison with the previous scenario, as now there are more buses and it takes up more space. Now then, the last part of the question is to calculate the average speed. So the average speed for the congested situation can be simply calculated by using the simple formula Q is equal to UK. So for the scenario before the transfer took place, it can be calculated by using the Q value, which is 1200, is equal to U multiplied by 104.17. This was the density found using average spacing in the initial condition. So based on that, the value of U can be found out to be 11.5 km per hour. On the other hand, after the transfer of vehicles, for this scenario, the new Q which we calculated was 862. So substituting that value as Q, and then U is unknown, and K can be substituted by the new density that is found from new average spacing, which is 96.9 vehicle per kilometer. So based on this simple substitution, you can find out U to be 8.9 km per hour. Last but not least, using the relationship Q is equal to kj multiplied by U minus kj over UF multiplied by U square. Now using the same volume, we can find the speeds during uncongested flow. So for the case where the transfer did not happen, substituting the values of Q as 1200 vehicles per hour, and then jam density as 121.69 vehicles per kilometer, and maximum free flow speed as 80 km per hour, we can find two values of u, which are 68.5 km per hour and 11.5 km per hour. Since we already found out that 11.5 km per hour is the speed during congested flow, therefore the speed during uncongested flow for the before case would be u is equal to 68.5 km per hour. On the other hand, for the after scenario, the values of q, kj and uf can be substituted as 862 vehicles per hour, and then for kj 109.02 vehicles per kilometer, and the free flow speed is 80 km per hour. Based on that, we get two values for speeds, which are 71.1 and 8.9 km per hour. And since we already found out that 8.9 km per hour is the average speed of road during congested flow, hence the speed during uncongested flow after the transfer of passengers from cars to buses can be found out to be as u is equal to 71.1 km per hour. So that's all from me. Thank you. Assalamu alaikum warahmatullahi wabarakatuh.
Good day and Selamat Sejahtera. My name is Abdul Rafi Balingdong, and today I'm going to explain about question 9 of the traffic assignment. So, a study of freeway flow at a particular site has resulted in a calibrated speed-density relationship as follows. K equals 60 multiplied by 2 minus 0.018 speed. Now, for this relationship, we need to determine four variables, which is the free flow speed, jam density, maximum flow, and speed and density when the flow is at a quarter or 1/4 of the maximum flow. And lastly, we need to sketch the flow density and speed density relationship to show all the relevant data of the values that we derive on the diagram, and state the traffic stream conditions of the diagrams. Okay, so let's start off with the first question. So for the free flow speed, we're going to use the equation that was given to us in the question, which is k equals 60 multiplied by 2. So derive the equation, which is 120 minus 1.08 u. Now, and after you derive the equation, we will get an equation which is u is equals to 111.11 minus 0.926 k. Now, as you can see from this equation, it's quite similar from the relationship diagram of relationships that we have studied, right? Which is this one, speed and flow, a speed and density relationship. Now, we can derive UF from this equation, which is 111.11 km per hour. Now, for the jump density, we can use the equation that we have derived from the first question, which is a free flow speed of 111.11 kph. We can also use the value of this one, UF over kj, which is 0.926. Now, since the free flow speed is already given, or we have derived it from the equation, we just simply substitute this in, transpose, then therefore we get the maximum of the jam density, which is 120 vehicles per kilometer. On to the next question. Now for the maximum flow, we're only going to use a simple formula, which is QC is equals to the free flow speed multiplied by the jam density over 4. So we get the value of 3,333.33 vehicle per hour. It's quite simple. Next equation. Now for the speed and density when the flow is at a quarter of the maximum flow. So earlier on the previous question, we have derived that the maximum flow is at 3,333.3 vehicle per hour. So if we need to find the quarter of the maximum flow, we just need to divide the maximum flow by 4, thus arriving at an answer of 833.3 vehicle per hour. Okay, so since we're asked to find the speed and density during the quarter of the flow, we're going to use the equations based on the relationships given to us in the diagrams that we have studied. Now for the speed, we're going to utilize this relationship. We're simply going to substitute all the values into the equation. Then we therefore arrive to the quadratic equation. So simply solving the quadratic equation, we derive with two answers of speed. Now later I'm going to explain in the last question why we have arrived at two different speeds. Now also for the density at the quarter of the flow, we also utilize a different equation, but it's also on the same diagram. with different type of equation. So we simply substitute in the values, and we also arrive at two different densities. Okay, so for the last question, we were asked to draw the diagram of low density relationship and speed density relationship. First and foremost, I'm going to start with the speed and density relationship. So as you can see, for the speed and density relationship, we start from the top, which is the maximum speed of the car, which is 111.11 kph. Now, as the cars continue to pass by, a lot of cars also occur at the same time. Thus, the density of the traffic flow gradually increases up until we reach the half of the maximum density, which is 60, and during that time we hit the critical speed, which is 55.6 km per hour. Now, when we reach onto this point, which is the maximum density, the maximum speed of the car significantly decreases at the point at 0. Now, moving on to the flow density relationship, as you can see that there's as a parabola, and there's two sides, the uncongested and congested. Now, as I said earlier, we have derived two values of speed and density. It's because when there's a higher speed, there's a lower density of lower volume density of cars, which is the uncongested. And for lower speed, while there is a maximum of jam density, this is the congested situation of the flow density relationship. So, okay, for the traffic stream conditions, the jam density is 120 vehicle per kilometer. The maximum flow of the traffic flow is 3,333 vehicle per hour, and for the capacity speed, it is at 55.6 km per hour. So that's all for me, and thank you for listening.